how to study the stationary distribution for a reducible Markov chain along with the assumptions. One is a periodic and the finite state. Here I am making one more, here I am giving the stationary distribution. So, I am giving the result for a reducible finite Markov chain. Markov chain is has in the finite state space and it is reducible one. With the close communicating class has aperiodic states, there is a mistake. A close communicating class of states has a aperiodic states. Aperiodic, the closed communicating class of states has aperiodic. Then the stationary distribution exists, that is going to be unique also, and that is given by the vector V, which consists of two subvectors V1 comma 0 vector, that you can find out. And this is nothing but the ergodic theorem for the reducible Markov chain with the assumption finite state space and the states of a close communicating class as aperiodic states. In that case, you will get the unique stationary distribution, and that unique stationary distribution has a two sub 1, that vectors are V1 and vectors of 0 elements. Before we get the stationary distribution, we can find out what is the n step transition probability for the same reducible Markov chain model. So, the Pn is going to be, you have a submatrix, stochastic submatrix P1, therefore, that is going to be P1 power n, whereas for every n this is going to be a function of n. R is the submatrix which is a one step going from the transient state to the close communicating class. Now, the Rn is nothing but a function of n, that elements that submatrix is corresponding to the transient state to the close communicating class, whereas the transient to transient, that is going to be a power n, that is a Q matrix. Q matrix is the submatrix for one step t to t, whereas the Q power n is the element corresponding to the n step transition probability matrix. So, as n tends to infinity, the stochastic submatrix, that power n, that will tends to E is the vector of V1, V1 is the sub few elements, that is corresponding to the stationary state probabilities for the states corresponding to the close communicating class of states. So, E is the vector of entities 1 1 1 and so on, multiplied by the V1, and the transient to transient n step transition probabilities Q power n, as n tends to infinity, this will tends to 0. This is obvious, because since the states are transient states, for a finite n you have a probability Q power n, whereas as n tends to infinity, the system will not be in the transient state. Therefore, the long run proportion of the time the system being in the transient states, that is 0 as n tends to infinity. Therefore, Qn will tends to 0, whereas this will tends to the stationary state probabilities. Therefore, this stationary distribution vector V consists of few elements of zeros, that is corresponding to the transient states, transient state probabilities in a longer run, and the V1 is the steady state probabilities in a longer run. It is not steady state, a stationary distribution, stationary state probabilities in a longer run for the close communicating class of states. So, this one can solve by using the equation pi p is equal to pi. You can get this pi a's, that pi a's is in the notation, here it is V i's V1. So, now I am making a further assumption that states are going to be a positive recurrent. So, already I made a a periodic states. Now I am making the one more assumption, it is a positive recurrent. Once it is a positive recurrent, then the limiting probability is limit n tends to infinity. That probability is going to be Vj's for the positive recurrent states, and for all the transient states the probabilities are going to be 0. And since we have a reducible Markov chain with one close communicating class and all other states are transient states, this stationary distribution or stationary state probabilities, these probabilities are independent of the initial state I. That means either the system can start at time 0 in the one of the states in the close communicating class or transient states. In the longer run, ultimately the system will be in one of the states in the close communicating class, whether it started initially from the close communicating class or transient states. Therefore, this stationary distribution is independent of initial state I. And for all the transient state, you can conclude immediately these probabilities are zeros, and for a positive recurrent states you can make it Vj's and you can compute these Vj's. Now, I am going to give one simple example in which we have a infinite state. This is going to be a reducible Markov chain because the states till 5, not till 5, including 4 and 2, the system come to the state 3. There is no arc from 3 to 4 or 3 to 2. Therefore, the states 2, 4, 5, 6 and so on, all those states are transient states, whereas the states 1 and 3 are going to form a one close communicating class. Therefore, this is the reducible Markov chain with the one close communicating class 1 and 3, and all other states are going to be the transient states. Therefore, as n tends to infinity, these probabilities are going to be 0 for these states 2, 4, 5 and so on, and these probabilities are independent of the initial state I. So, wherever the I, whether the I is belonging to the one of the elements, one of the states in the close communicating class of states or transient states, immaterial of that, this is stationary distributions are zeros for the transient state. For the close communicating class of states, you can find out this probability by separately making the Markov chain. The states 1 and 3, you can make it separately, and there is a arc from 1 to 3 with the probability of, there is a self loop with the probability 1 by 2, and there is a self loop in the state 3 with the probability 1 by 3, and the arc from 3 to 1 is 2 by 3. So, what do you want to find out? This stationary distribution for these two states. Therefore, you make a stochastic submatrix with the states 1 and 3, that is 1 by 2, 1 by 3, 2 by 3 and 1 by 3. This is also stochastic matrix, you can verify. Now, if you want to find out the stationary distribution for these two states, you solve pi p1 is equal to pi. That means pi 1 pi 3 times p1, that is 1 by 2 1 by 3, oh sorry 1 by 2, this is 1 by 2, 1 by 2 1 by 2, and this is 2 by 3 1 by 3, that is equal to pi 1 pi 3. You take the first equation, that is pi 1 of times pi 1 plus 2/3 pi 3, that is equal to pi 1. So, from here you will get pi 3 is equal to 3 by 4 pi 1. Now, you use pi 1 plus pi 3 is equal to 1. So, using this you will get pi 1 is equal to 4 by 7. Once you know the pi 1, the pi 3 is going to be 3 by 7. So, you do not want to find out the stationary distribution for the whole model. Instead of that, you can find out what is the close communicating class, and you can solve only the close communicating class, that submatrix pi p 1 is equal to pi, and you will get pi 1 and pi 3, and that is going to be in a longer run, that is equal to 4 by 7 and 3 by 7, and all other states are going to be 0.